Welcome back, everyone. We now proceed with our next talk by Mr. Niraj Bhukhanwala. Mr. Bhukhanwala is an accomplished entrepreneur and the managing director of Bhukhanwala Industries Private Limited, a leading manufacturer of high performance ceramic solutions for defense, nuclear, and aerospace applications. Under his leadership, Bhukhanwala Industries has been involved in strategic projects with prestigious organizations such as Department of Atomic Energy, DRDO, and ISRO. In addition to his work at Bhukhanwala Industries, he has also founded two startups, Agrima Advanced Materials, which develops advanced ceramic solutions for the semiconductors and energy industries, and 6C Nanocarb Private Limited, focused on advanced carbon-based product utilizing carbon nanotubes and graphene. Before joining the Bhukhanwala Group, he was part of the founding team of Intel Capital in India. He also worked as a managing consultant at McKinsey, focusing on wireless technology and healthcare. His talk will be centered on high-performance ceramics for strategic applications, defense, nuclear, and aerospace. Let's welcome him on the podium.
Professor Patwardhan, the rest of the delegates, students. So it's great to be back to the alma mater, to come here. Every time I come here and speak, I feel nostalgia walking on campus. So I know the crowd has thinned out, but I'm going to talk about high performance ceramics, how they fit into the strategic domain, and why material science is actually critical for anything that we talk about, self-reliance, everything that General Pandey talked about and Air Vice Marshal Court talked about, that unless you have access to critical materials, you'll never be truly self-reliant. So I come from the world of ceramics. Ceramics is a material that is neither metallic nor organic. It may be crystalline, glassy. So it's a wide range of properties, wide range of applications for ceramics. And as we like to say that, ceramics start functioning when metals stop, right? So whether it's high temperatures, which metals can't withstand, hostile, chemical, harsh environments, that's when ceramics come into play. We classify both of them, non-oxide and oxide ceramics, both are important for different applications, but both have very different ways of synthesis or processing. So a completely different range of processing technologies are used for these. I'm going to skip this. So non-oxide ceramics, so that's been our main focus. We're now getting into oxides, but non-oxides are really what we've been involved with since our inception. These are carbides, borides, nitrides of boron, silicon, titanium, zirconium. They have very unique properties, very high hardness, excellent wear resistance, and as well as oxidation resistance. And I'll be spending more time on boron carbide. That's our flagship product, which has very high hardness, low density, great nuclear properties in terms of neutron absorption. So it has applications both in defense and nuclear. There's boron nitride, which we are now working with ISRO and through a technology transfer are now actually making product that will be used in the Indian space program. Silicon carbide, again, very widely used commercially as well as in defense environments. Titanium diboride, again, excellent material for both wear resistance as well as nuclear application. This is something that we are now beginning to make under a technology license from BRC. And similarly, zirconium diboride is a material of interest for hypersonic vehicles, re-entry vehicles. So just a small table of materials. I've tried to map out some of these ceramic materials and where we are seeing their applications. Of course, this is not exhaustive. There'll be probably more applications. So for boron carbide, on the defense side, you have boron carbide, silicon carbide, alumina, which are being used as armor material, both for body armor as well as for vehicle or aircraft armor. You have zirconium diboride, which is something that's being used for ultra high temperature applications. So when you're looking at re-entry vehicles or hypersonic vehicles, there's work happening on that. On the nuclear side, boron carbide is an excellent material for neutron shielding. And one of the things that I'd like to point out is when we are talking of AI, ML, if you see the amount of energy that is required, the investment that you're seeing globally now on nuclear reactors, both fusion as well as small modular reactors, you cannot make a reactor without using boron carbide. So for us, the last few years of growth have come from the nuclear renaissance that we're seeing in the world. And so everything that you talk about, whether it's the energy sector, it requires ceramics. Whether it's the defense sector, it requires ceramics. So this is more a pitch to all the people studying material science that you can remain in the core. You don't have to move towards AI ML. You know, AI ML will require all disciplines of engineering to contribute. Similarly, silicon carbide is again a very interesting material on the nuclear side. So if you look at all the tubes that are used for the thermal systems, use that. You have very high density parts that are used as seals for the pumps of nuclear reactors. Aerospace, again, silicon carbide, silica are used in some of the thrusters, heat resistant functions. We are doing a host of electronic ceramics. So these are all oxide ceramics where you're making resonators, your oscillators. So these are ceramics that are functioning at different frequencies. And we are working very closely with ISRO to do that indigenously. This is a center we'll be putting up at IIT Bombay Research Park. And boron nitride composite. So boron nitride again is a unique material where it's an electrical insulator but a thermal conductor. So it's used inside your Hall effect electric propulsion systems. Your liners for the Hall effect thrusters are made out of this. This is now a flight qualified component that we have made with ISRO's help. And from this year, it will replace American liners in the Indian space program. So this will be made in India for Indian satellite launches. I think this has stopped. Can you? You can just go to the next slide, please. So yeah, just one slide back. So we, like I mentioned, we are focused only on strategic applications. We do defense, nuclear, aerospace, and we are beginning to do some work on the semiconductor side as well. We're the only manufacturer of a complete range of boron carbide. So from synthesis of powder itself, which we have a technology license from Baba Atomic Research Center, to finished hot press components being used for both nuclear and aerospace. We've done a lot of strategic projects in India. So on the fast breeder reactor being built at Kalpakam, that's really the genesis of how the company started, was to support that requirement. And under the technology denial regime, BRC had no alternative but to work and develop that indigenously. So that's really what developed the capability at our end. And we are also supplying into, there are, I'll talk about this later, but some body armor designs that have been made by DRDO as well as by BRC for the Indian security forces are based on our ceramics. On the nuclear side, we're already working on the fusion side. Fusion, I think you read every day about new records being set by various experimental reactors. So fusion is a huge source of revenue for us. CFS is a spin out of MIT. It's actually the world's largest funded stage Series B round. They raised $2 billion for Series B to build a prototype fusion reactor. It's called the Spark. And we are supplying all the neutron shielding components into that. We've already supplied over $15 million to them, and there's another 10 million in the pipeline. We work closely with ITER. This is where Prime Minister Modi had recently gone to France. So we're working with different ITER units. Again, they will require huge amounts of shielding. So as a material, this is a great material to be in and to scale up. We are also working with some of the small modular reactors. So a number of speakers have talked about that if you look at the requirements, and India has also announced a policy. So small modular reactors again will require a huge amount of ceramics, both for shielding as well as for thermal management. On international defense, our focus has primarily been on aircraft armor. So boron carbide is a very light material, and so for aircraft platforms, that weight is a premium. So anything that when they armor, so some of our customers are making seats for the helicopters, and the pilot and co-pilot seat are ballistically armored, so that when there is small arm fire, it protects the pilot and co-pilot. So the ceramics are used in that context. We're already on a number of platforms. We're on the Apache AH-64. We're on the Boeing V-22 Osprey. We'll be getting onto the CH-53K soon as well. We're on a couple of Augusta-Westland platforms as well. So our idea is, we are a global leader in boron carbide solutions. We want to look at strategic, expand our material portfolio, and my next slide will talk about that. So we are a good model of taking a technology that came out of a government lab, really productionized it, scaled it up globally, and we want to replicate that with other technologies, other materials that we are licensing. So like I mentioned, we have boron nitride is something that we have licensed from ISRO. And once it successfully flies on the Indian space program, we hope to take it to the global private space market with SpaceX, etc. We're doing, as I said, electronic ceramics again with ISRO, where these are going to be used within the communication circuits, both on the satellite as well as the ground stations. So this again is a huge market. The Japanese dominate this. So hopefully we'll be able to break into that global monopoly. So this is again a list. This was just to kind of list out that the range of ceramic materials itself is so large for strategic applications that there is enough growth both in terms of doing research work as well as in terms of building careers on. This is how we are. We have a corporate office in Mumbai. Our manufacturing facilities are in Navsari, so we are very close to Surat. We are right now tiling up our lab at the IIT Bombay Research Park. So our lab at IIT Bombay Research Park should be operational in the next 3 months, delayed because of the OC delays. And we are, depending on how we see growth, we will be looking at building a second campus in the Vadodara-Ahmedabad belt because a lot of our US defense customers want geographical diversification because we've become single source for them. They would like to have a separate unit so that if it's earthquake, flood, they want to ensure that there is a separate unit that's operational. They don't want all the production to happen in one. Again, it's something that we're looking at maybe 4 or 5 years down the line. Our engagement with IIT Bombay, so we are calling our lab at Research Park Prism, so path-breaking research and innovation in strategic materials. It'll be focused on electronic ceramics for space and defense, and we'll also have a lab that's focused on advanced carbon technologies there, where we're doing work on carbon nanotube sheets as well as carbon nanotube fibers. These are again technology licenses from BRC. We recently signed an MTech fellowship program with IIT Bombay. So a second year fellowship will be funded by us over the next many years. And students will be able to choose a project related to advanced materials with strategic applications. I think the first student has already been shortlisted by the institute, and we'll be doing work on substrates, alumina-based substrates for the space program. So just a very quick introduction to boron carbide. Strategic applications, like I mentioned, in defense and nuclear. Boron carbide is a unique material because it stops bullets and it stops neutrons as well. So it's one of those few materials that is used in both applications without any change in form. Its lightweight and high hardness make it ideal for body armor or any other armor applications that have weight constraints, and it's expensive. It's a very, very expensive material, and we have this constant engagement or arguments with the Indian users. As the gentleman in uniform will appreciate that we always want the lightest, but we don't want to pay for it. I always tell them that we are the lightest, like to like, we're the lightest, we are the cheapest in the world. But there is a certain intrinsic cost to the product which cannot be brought down. And so we are working on developing alternate materials for mass requirements of the army. For this, in fact, there are a small quantity of body armor jackets were made using our ceramic for the special forces in the Northern Command under emergency procurement by Tata. But again, because the quantity was small, budgets were not a constraint. So they have actually been used, but we haven't been able to translate it into kind of mass just because of procurement procedures, budget sensitivities. Like I mentioned, we do the entire range of powders. For nuclear applications as well, we're supplying globally. And I think India needs to catch up on both the fusion and the SMR side. We are falling behind. The amount of startups that we're seeing in France, in Europe, in the US for nuclear is fantastic. And I think we're being left behind on that. So I think you can't really have strategic autonomy unless your energy sources are secure. I'm going to quickly run through just some of the platforms like I talked about. We're on the Apache, on the Osprey. We'll be on the replacement for the Osprey, which is the FLARA, which is the future vertical lift platform that the US is making. These are some of the ceramic parts that we make. These are all built to print with complex features. So because they go onto the seats, they have to match with the metal frame of the seats. So this is something that we cut to size here and ship to the US, where it gets integrated into the final product. Some of the platforms that we are on, like I said, we are on the Apache. We've already supplied into over about 180 helicopters already, and we have a new contract for another 336 sets with the US. We are on the Osprey, which is now kind of winding down. We are on a FutureLinks platform as well. We will soon hopefully be on the ALH and the LCH as well. So that's something that we're working with the Indian ecosystem to get our ceramics on the Indian helicopter platforms. There are two initiatives in India to make body armor, lightweight body armor. One was through BRC, which is called as the Bhaba Kavach. This was something that used our ceramic, used carbon nanotubes in the polymer, and they developed a very good solution. Medani, which is a DPSU, is a TOT holder, and they've been supplying some amount into the armed forces, though it has not really scaled up, again, for price concerns. I believe there is now an engagement with the Navy and BRC to get that done. And again, I think it's a great solution, very well designed. I can send these slides to you. I'll have the organizers send that to you if that's. So this is a mosaic design designed really to take a high number of shots, right? So because ceramics are brittle, when a bullet actually hits, you have cracks and it propagates. So if it's a monolithic ceramic, you can maybe take 2 or 3 shots before which it starts splintering. By using a mosaic design, each individual tile becomes a separate system. Because there is a small air gap, the crack doesn't propagate. So these have been shot for very high burst fire rounds and has performed well. Makes it expensive. So again, I think it's about how we write our QRs, that if you ask for very high multi-hit requirement, if you may not need it in operations, you're adding both weight and cost to that. Similarly, there is a recent technology that was announced by DRDO and IIT Delhi called Abhed. There was an MOU signed recently by the Raksha Mantri for 3 technology holders to take it. This again is based on our boron carbide ceramic. I'll talk a bit about at a policy level, how do you take these solutions in the armed forces. A very good solution. This is designed for API rounds, so BI6. Very extensively tested by IIT and DRDO. And so hopefully this will translate into usage by the forces. With this constant cost pressure, we are now introducing, and this thing has not come. Okay, so I'll just talk through this. So we are introducing direct sintered silicon carbide, so it should be substantially cheaper. It'll be maybe slightly heavier than boron carbide, but it'll be substantially cheaper and should pretty much, if you take the mobility and weight requirements of special forces out, this should actually work for the majority of the forces. The US Army as well uses this material as a material of choice for its bulk infantry, and keeping the very lightweight solutions only for the the Green Berets or the Marines. So I think that's the right way for even the Indian Army to look at it, to have a differentiated QR for weight, so that you can, you are not forcing the special forces to use the lowest common denominator on price. Just a very quick slide on what we're doing for the space program. So we're doing a number of ceramics. Sorry? So these are all for kinetic threat. They're not really designed for explosives. So it's really for small arms bullet fire, right? So like I mentioned with ISRO, the electric propulsion systems will now soon use liners, and we are very excited with the whole private space industry, so that once it goes on ISRO flights, then we can cater to all the startups that are here as well. The other thing that we're doing, which is quite interesting, is again, this is a replacement of a Japanese terminal seal. So the satellites all use lithium-ion batteries for their power requirements on board, and the terminals of the batteries are made using diffusion bonding. So you are able to join a ceramic and a metal, but without a third braze layer. So you take a ceramic, you take a metal, you subject it to temperature, pressure in very high vacuum, and at the interface you actually have a molecular level diffusion. So you have the ceramic molecules diffusing into the metal and the metal molecules diffusing. That bond is extremely strong. Very expensive solution, so obviously not a solution for the cars, etc. But in the space environment, this is fantastic, and we've been able to develop this at 1/3 the cost of Kyocera. So right now it's in final flight qualification at ISRO, and they will soon start phasing this out from imports. I'll kind of skip some of these. So these are some of the parts, like I said, aircraft armor. These are the thruster that I talked about. Some high purity alumina cones that we're making again for the nuclear program. So where you have a high plasma environment, you have the ceramic facing the plasma side, and then you have the metal on the other side. We're doing some sputtering targets. Again, this is something that we have now stepped into as our kind of segue into the semiconductor industry. We're beginning to export sputtering targets to the US and Europe. And our idea is to develop more sputtering targets with IIT Bombay's help, look at different materials for that. IIT Bombay itself imports a lot of sputtering targets, so that's why our plan is to first start working with your needs, try and develop the sputtering, high purity sputtering targets in India, and then kind of benchmark its performance with imports, and then start exporting. Electronic ceramics is what I talked about. So BMT is one particular material composition. We now have 5 different compositions from ISRO, all operating at different frequency ranges, including what will be used for the NAVIC chip as well. So we've got that technology transferred as well. And this was the terminal seal I talked about. So the white thing that you see is alumina. This is aluminum. And you're able to join those two without any braze layer. It's a unique technology developed by ISRO. And we are hoping that we can use this technology to join 2 dissimilar metals or different combinations of ceramics and metals. It has a lot of application. Right now the system is a very small one, so we can do very small components, but the technology itself has great potential. So I would just a few minutes to talk about what I think is important for policy-wise to look at strategic materials. So I think what we really need as a country is to have a national strategic materials policy. What are the materials that are critical for us as a country? And when you look at defense, nuclear, aerospace, as you know that China has a monopoly on all rare earth metals, and this whole Ukraine war is eventually going to end up with the US and Russia getting access to, that probably could be the underlying reason for it, right? However, as a country, we don't seem to have any long-term vision on what's going to be needed to secure these materials for us, right? Today, when we make boron carbide powder, we are still dependent on boric acid, which is imported, because there has not been really any exploration done with the boric acid, which is a mined mineral, whether deposits exist in India, and if so. So right now, most of the materials coming from Turkey. They have one of the largest mines. You have mines in Latin America. Now, if such a critical material is going to be imported from Turkey, where you have, you're not really sure whether it's friend or foe. So I think we need to think longer, a bit further in terms of how would we secure the supply chain if things go wrong, right? So I think when Parikar sir was there, he started this National Strategic Materials Policy, and then I think post his demise, it has just kind of withered away. It may be important to get focus on that and focus on what is critical. Let the users define what materials are critical and build capabilities. And as AVM code said, it's not just capabilities. You have to invest in capacities also, right? So one is to make something, and then is to make something at scale, and that requires the government to fund, right? The government needs to fund capacity building within the country. The US has a very good model for that. Within the DoD, they have an office for industrialization, and they have a concept called LRIP, low rate industrial production. So even if the armed forces don't need something, to keep those factories running, the US DoD will give them a low rate production so that the lines keep working and you don't lose knowledge. Because you cannot expect these strategic industries to move tender to tender and war to war. And so that's a very, very important concept for any strategic platform that they make, any component, they have LRIP as a concept. They will at least ensure that if you have 2 lines, 1 line will run, even if they don't need the product. They will stockpile it if needed, so that you are not losing industrial capabilities. The flip side of that is what has happened to Europe, right? As Mr. Nilesh was saying, Europe has pretty much lost all its industrial capabilities because they decided, we don't want to do nuclear, we don't want to fight wars, and they just shut everything. So you can't turn on capacity building overnight. So this is something that we have to invest it and kind of sustain over a longer period of time. Accelerate technology transfer from government labs, that has improved substantially. So while I put this up, in the last 5-6 years, we've seen it has, with InSpace is there, DAE does a very good job, DRDO does a very good job as well now. But I also think that we need to start minimizing technology transfer fees. Especially out of DRDO, what we've seen is that earlier DRDO technologies used to be priced very nominally, right? And you charge a royalty. Of late, the costing model has changed where the price is determined as saying, okay, so many crores was spent to develop this technology, let me recover this from my license fee. But DRDO or DAE or ISRO are not for-profit research centers. The taxpayer has funded it. The aim should be to proliferate that technology, not to recover the cost that the government has made. So I think that's, for me, that's a bit of a contradictory thought. You've developed technology, give it to as many people as, obviously you vet them, but give it to them, make it affordable for startups so that they can go out and build applications on that. And lastly, multiple speakers have talked about it. Create a seed fund for technology which has longer gestation periods. The time frame of traditional venture capital and private equity funds may not really work for strategic applications because the time cycles are too long. So there has to be a different way to fund these deep tech startups through different kind of money which is patient, which looks at national importance as a metric and not just returns. So that's just it's a wish list. Since I have the forum, I might as well put the wish list out there. Sorry? No, SIDBI also, but yeah, no, I think what you need is patient money, right? So you have to find someone who's going to be patient, and the government has to be that. Only the government can fund that. Just a specific case, and this is the last slide, that how can you support, say, strategic material, the strategic materials industry in India? So when I look at body armor, it's now been put on the negative list where body armor has to be made in India, right? But it still doesn't go far enough to say that the critical components that will be used to make body armor should be made in India. The US actually has that. The US has the Berry Amendment. It's the act of the US Congress. So today, I cannot sell my ceramic to a US body armor program because it is not allowed by law. That's why only the aircraft armor is open to us. It says that for all body armor, either the ceramic must be made in the US. And as a result, we are actually looking at setting up a facility there so that we can capture the, play into that market. So what our suggestion is that there is enough ceramic capability within the country. There are multiple players, including us. I'm not saying I'm the only one there. There are other players doing different kind of ceramics. If you say that the ceramics must be made in India for whatever the army and the MHA buy, then that capacity building will happen automatically. It is not possible to build ceramic capability going on a tender to tender basis. We need to have the ability to have some forecast. It's very capex intensive. So we need to have a 10-year visibility of saying, okay, 10 years, this is the amount of components that will be used and we can invest in those capabilities. And the US actually has been doing this for decades now. So it's not that we would be the first country to do it. So I think we need to go that one step further, not just look at indigenous content percentage, but also say that critical items that will be used will actually be made in India. There was a recent news article about this drone contract that got cancelled because a lot of the components were Chinese. But ideally, we should actually build that into the tender conditions so you don't have contract cancellations later. So again, this is my wish list, and I've been saying this at various forums, whether it's Niti Aayog or not. So hopefully it'll get translated someday. But that would give us that confidence to invest in capacities to cater to the Indian needs. Currently, our capacity building has happened primarily from US long-term programs so for the Apache, I have a 10-year long-term contract, which allows me to actually invest in capacity because I know कि 10 साल में इतना तो लेगा ही. So it's ironic that I have US customers funding capacity building in India, but we are not getting that support from the Indian ecosystem. So that's all I had. Thank you for the opportunity.